Hello students, Mr. Hatfield here. Hope you're still enjoying your vacation. We have a few days before we go back, but I thought I'd go ahead and make a video demonstrating how to use the Density Exploration GIZMO. I did show this before we went on break, but I thought it'd be a good idea to do it since so many of you still haven't handed it in and it might be time for a little refresher. So let's get after that right now. Remember, in order to access gizmos, we're going to need to go to explorelearning.com. We get there, we'll log in, just like I'm doing. And once you're logged in, you'll choose your period. In my case, I'll just go to period 6. It really doesn't matter. We'll go here to the bottom where it says Density Laboratory. We'll click on the rocket icon to launch the gizmo. Now, when we look at it, we see that basically there are 3 parts. There's a shelf that has a variety of different sized and shaped objects that are draggable. That is, we can move them around on the screen. Just click on it and move it around. And then we have the second part is that we can determine some facts about our objects. We have a scale to measure its mass in grams, and we have a graduated cylinder which is filled with 400 milliliters of fluid. And we can use this to figure out the volume of these irregularly shaped objects. Finally, we have a supply of a fluid. Here we happen to know that the fluid is water. How do we know that? Because the slider here is set to 1.0, exactly 1. That's 1 gram per 1 milliliter. It turns out that if you're the substance that is 1 gram of mass per 1 milliliter volume, well, you're water. Yeah, that's right. The metric system has been rigged so that the standard for density is water, and it's exactly 1. Kind of convenient. Less obvious, but also convenient. Objects like this, solid objects, are measured in cubic centimeters. That is, we measure how high something is, how wide something is, and how deep something is in centimeters, and it's centimeters times centimeters times centimeters, so we say centimeters cubed. Now that's pretty easy to do for something like a cube, because in a cube each side is the same length. So if you had 2 centimeters for each side, it'd be 2 times 2 times 2, or 8 cubic centimeters. A little bit harder to do perhaps if you have a rectangular solid, one side will be longer than the other. And if you're a cone, you need a different formula that's going to involve an irrational number pi. And then for these irregular egg shapes, well, those are quite a bit harder to figure. You have to figure the area under the curve. So, there's a way to measure or estimate the volume of these objects with a variety of formula and math. But what about these objects at the bottom, these very particular objects that have very complex shapes? They're crowns. There is actually no mathematical formula for these various different crowns. And so how does one go about determining the volume? Business with the crowns is relevant to the last part of the exercise, which references a very famous historical case, an actual story that really happened, where a Greek genius who lived 2,500 years ago named Archimedes was challenged with figuring out something about a crown that involved determining the volume of the crown, and yet it was an irregular shape, and he wanted to figure it out. So we'll get to that in a moment. That's kind of the high point of this exercise. But first we'll practice with these simpler geometric shapes. Okay, so let's take an example. Let's take this object right here, which is kind of gold colored, and we'll put it on the scale. 134.8 grams. So if you were choosing that object number 4, you would record that mass. We can take that same object by clicking on it, and we can put it into the graduated cylinder. Now again, the liquid shows 400 milliliters. But if we release the object, it sinks, and we see that the level of the liquid goes up. It goes up from 400 to 407.8. That is, it goes up 7.8 milliliters. Well, look at this. That means the object is 7.8 cubic centimeters. Now again, the cubic centimeters here is an object of solid volume, but we just measured a change in the liquid volume. And so this is another remarkable thing about the metric system. Not only does the metric system have it set up so that water is the standard for density, and it's exactly 1, but the metric system also has rigged it so that a unit of liquid volume, the milliliter, is exactly equal to a unit of solid volume, the cubic centimeter. Now this is very convenient indeed. And so you'll be able to take the mass and the density of various objects. Now again, if we take this relatively massive object, this little gold chunk, and we put it in water, well, no surprise, it sinks. And, you know, if we take, say, one of these crowns that we'll use later, you know, probably made out of metal, well, no surprise, it sinks. But what if we take this rectangular solid? Well, it sinks a little bit, but it doesn't sink very far. It doesn't sink as far as the other objects do. It goes down a little bit and then something stops it. Or we can take this cone and it doesn't sink at all. So something interesting is going on here, which is that two of the objects were sufficiently massive, had high enough density that they sink right away to the bottom. Nothing could stop it. The rectangular cube, the red solid, sank a little bit, but then it stopped, as if the water was pushing back against it, but not completely. And then the green cone, why it didn't sink at all. What we're going to do now is we're going to adjust the slider. And this would be similar as if we were adding something to the water. Like if I took salt and I dropped it in the water, you know and I know the salt would dissolve. Less obviously, the mass of the salt would be added to the mass of the water, which means it wouldn't be fresh water anymore, but it would have a greater mass in grams, and so therefore its density would go up. Let's pretend we add just a little bit of salt to this water, just a little bit. Hey, did you see what happened there? That was kind of interesting. Let's go back to 1. Let's go back to standard for 1. Look very carefully at the items floating on the top. As we add salt, as we move the slider, we add mass to solution, we see that the rectangular block rises higher and higher. That's because the solution beneath it is becoming more dense, which means it's pushing back more. In fact, if we push back quite a bit more, we can get that rectangular solid to float. Oh, and look at that. The crown goes up. What would happen if we go down a little bit? Well, now you see the crown is slowly going down. So now if we raise it up just a little bit, just a little bit, just a little bit more. So you see what's happening there. We're getting to a point, we're approaching a point which is about the same as the mass of the crown. And so if we lower it just a little bit, it goes down. If we raise it just a little bit, it goes up. And so that means that must be very close to the actual density of the crown. Okay, so let's now talk about Archimedes. Archimedes was tasked with figuring stuff out about these crowns. And he was tasked by his lord and master, who was the tyrant of Syracuse. Syracuse was a city in the ancient world that was on the coast. Wasn't a very big city, but it was a very rich city. And its greatest treasure was the mind of Archimedes, who was a great genius, probably one of the smartest people who ever lived. Archimedes was somebody who acted like a scientist before science was even invented. We know this because he actually kept notes and described experiments that he did in detail. And there are many legends about the things that Archimedes was able to do. Now, the tyrant of Syracuse was, well, he wasn't as smart as Archimedes, but he was the king, and he was kind of an ill-natured fellow. That is to say, if you crossed him, it was off with your head. Anybody who didn't act the way he liked, well, he might take their head off. He was a tyrant, right? And he suspected that somebody had cheated him. He'd had a crown made. He had many crowns, but he had a new crown made. It was supposed to be of pure gold. And he suspected that they were cheating him. So he went to Archimedes. He said, "Come here, Archimedes. You're the wise one here. I want you to figure out if this crown is actually pure gold or not. I need to find out if these people cheated me. But don't damage the crown. I don't want you to cut it open to figure it out. You got to come up with some other way to figure it out. I'm sure you can do it." And of course, you're the smart one here, and I know you can do it. And of course, the implied threat was if you don't do it, off with your head. So Archimedes wasn't sure what to do, but he went to the baths. Now, the legend goes that Archimedes had actually constructed great public baths. He had figured out way back in the day, 2,500 years ago, he had figured out how to bring water from the surrounding hillsides and how to heat that water so that people like himself could have a warm bath anytime they wanted to. So he went to the public bathhouse, and as he got into the bathtub, he noticed that as he got in, that the level of the water in the bathtub went up, just like it goes up when we drop something inside the graduated cylinder. At that moment, he had a flash of insight. He realized that his body was an irregular object, just like that crown, but that his body was pushing aside the water, and the amount of water that he was pushing aside had to be equal to the volume of his body. So he had figured out in his head how to determine the irregular volume without doing a whole bunch of fancy math. And so Archimedes was able to test the various crowns that the king asked him to test. He figured out how to do it, and you're going to do something similar. I'm not going to say any more about that, except that this really did happen, and Archimedes really did figure out how to solve the king's problem and address his concerns, and you'll do something very similar. And so that's the task that you have before you, and I'm sure you'll be able to do it, but you need to do it in a timely fashion. You're currently on break. We come back on Monday the 30th, and then anything that was assigned before the 30th, well, it's due, and then we need to go on. And when we come back, well, there'll only be 7 days of instruction left. And so we are nearing the end of the semester. So it's important that we don't fall behind and that we get our work in order to complete the course. All right, thanks everyone for listening, and I appreciate the work you're doing, and I look forward to seeing the work that you send to me in email. And take care until we meet again. Bye-bye.